The moniker itself is the main feature that characterizes black holes. Black holes are just that, black. At the event horizon, the gravitational force is so strong that light cannot escape. Black in this context denotes a lack of light. However, we also associate black with the lack of color. As long as you mean quantum chromodynamic charge, it turns out that it is possible to create a colored black hole. We are certain that there are two primary kinds of black holes. Some stellar black holes have masses ranging from 10 to 50 times that of the Sun. With event horizons that are only tens of kilometers broad, these are the remnants that remain after the most massive stars die in supernova explosions. They are astronomically small objects. Next are the supermassive black holes found in galaxy centers. These objects have diameters comparable to those of solar systems and weigh millions to billions of times the mass of the Sun. Since mass affects the size of a black hole's event horizon, it appears to be the most crucial characteristic that sets them apart from one another. The second most significant factor is a black hole's spin, which tugs the fabric of space around a black hole and squishes the otherwise spherical event horizon. However, black holes can only have three characteristics: mass, spin, and charge, according to Jacob Bekenstein's no-hair theorem. We have now discussed spin and mass. What about charge? The electric charge that shocks you when you drag your feet on the carpet and then touch a doorknob is typically what comes to mind when we think about black hole charge. Black holes swiftly draw and neutralize the opposing charge from matter in the surrounding cosmos, making it difficult for them to retain electric charge. If you will, they are in contact with the cosmic doorknob. The no-hair theorem's charge, however, is not limited to the positive and negative electric charges that are sensitive to electromagnetic force. Any charge that corresponds to one of the basic quantum forces is referred to by this term. Could these stranger forms of charge be retained by black holes? The strongest force's so-called color charge is the most plausible explanation for a black hole's charge. We have episodes about the strong force, color charge, and quantum chromodynamics, the theory that explains it. To put it briefly, the strong force holds quarks in atomic nuclei and protons and neutrons together. Electric charge, which can be either positive or negative, is the only kind of charge connected to electromagnetic interaction. However, the powerful force has three different kinds of charges. Their negatives are anti-red, anti-green, and anti-blue, and they are named after the hues red, green, and blue. Although the name isn't wholly poetic, they aren't these colors in reality. In this video, we explain the deeper link between visible colors and strong force colors. From a quantum chromodynamic point of view, we should be able to have a red or anti-blue black hole, as the no-hair theorem states that black holes can display any of the charges of the fundamental forces. But are these things actually real in the universe? And if so, could we be able to discover some genuine influence they have on the universe? The answer is both yes and yes, according to a study that MIT professor David I. Kaiser and PhD candidate Elba Alonso Monsalve released in May. Or maybe. You have most likely never heard of color-charged black holes since, on the surface, they shouldn't exist. As I explained, electrically charged black holes neutralize themselves, hence they aren't actually real. It should be significantly more difficult to create color-charged black holes. This is due to a phenomenon known as color confinement. An isolated color charge, such as a single quark, cannot be observed in nearly every setting in the current cosmos. In order to create color-neutral objects, or hadrons, all color charges must combine. As a result, you will never witness a single green quark. Instead, you will see a proton or neutron made up of a green, red, and blue quark bonded together. Or perhaps a meson with a red and anti-red quark. These hadrons, or quark composites, will cancel out to zero color charge due to their color combination. These confined particles are never given the opportunity to accumulate color charge as true black holes expand from consuming them. However, this does not imply that color charge separation is impossible. At temperatures below 10 trillion Kelvin, color confinement is effective. Individual quarks and gluons, however, are free to move about in a quark-gluon plasma above that temperature since they are no longer bonded. There may be small areas of more green, anti-red, or another color in such a plasma. Presumably, we could produce a color-charged black hole if we could produce one inside such a region. As it happens, the universe was once filled with a quark-gluon plasma, and it is possible that a large number of black holes originated during that period. It makes sense that the most natural thing in the universe used to be bright black holes. Thus, the universe was a very hot and dense soup of matter and radiation immediately following the Great Bang. Additionally, it was very little clumpy, a little more matter here, a little less there, fluctuations that, because of their slightly higher gravity, pushed on nearby material, eventually growing into cosmic background radiation bumps and, eventually, galaxies. However, in certain places, the density changes were sufficiently high to accelerate their growth. Fast enough to create black holes. Primordial black holes are these initial black holes. Although we haven't identified one, they might be present everywhere. We produced episodes on PBHs, of course. PBHs might conceivably have any mass because they weren't formed from the cores of dead stars. They range in size from a millionth of a gram to hundreds of thousands of times the mass of the Sun. They might have been the earliest seeds of supermassive black holes and could help explain how those objects grew so large so quickly if they started at the massive end. They might be a good fit for dark matter if they are lighter in nature. The precise moment these objects formed in the first second or so following the Big Bang determines the mass at which they did so. There should be several tiny PBHs if it's early. There should be fewer but larger ones if it's later. Alright, so the universe might have created a great number of black holes under the harsh circumstances of that initial instant. We have the prerequisites for colorful black holes if the black hole production occurred on the early side, inside the first 100,000th of a second. The temperature of the cosmos was higher than 10 to the power of 13 Kelvin, which is the temperature at which quark-bound states are impossible, prior to 10 to the power of -5 seconds. In those days, the quark-gluon plasma, a mixture of free quarks and gluons, filled the entire cosmos. Even though this plasma has no net color charge, if you look closely enough at small patches, you may see areas that are sometimes slightly more of one color than the others. And we would have our color-charged black hole if such areas were thick enough to collapse into a PBH. The goal of this new study's investigators was to determine whether and how many of these color-charged PBHs might exist. However, in order to ascertain whether they were small enough to capture one of these little color-charged patches of the quark-gluon plasma, they first needed to know when these things formed. Keep in mind that the formation time dictates the size of the PBHs. To determine that formation period, these researchers make another assumption. I said that some people believe dark matter could be explained by PBHs. However, our observations have ruled out the existence of many black holes outside of this range, thus it only applies to a small range of primordial black hole masses. That range, or 10^14 10^19 kg, is approximately between that of a small moon and a medium asteroid. PBHs must fall within this mass range and have developed between 10 to the power of -21 and 10 to the power of -16 seconds after the Big Bang, which is the formation range that the researchers take into consideration whether they are dark matter. If PBHs created at that time were small enough to fall into one of these arbitrary color variations, they might have color charge because the cosmos was still well within the quark-gluon plasma era. Regretfully, if PBHs had formed at this time, the majority would have been too large to absorb any significant amount of net color charge. Color neutrality would have been generated by such PBHs. However, colorful black holes are still a possibility. Not all black holes with the same mass form, according to one of the primary theories for PBH formation. Instead, there is a peak mass, the mass that would make the most contribution to dark matter. However, these larger black hole masses should be accompanied by a lengthy tail of ever tinier ones. In fact, some of these would be sufficiently tiny to absorb a sizable amount of color charge. Alongside the larger, neutral PBHs that would eventually become dark matter, the researchers' scenarios should have produced a vast number of microscopic, colorful PBHs. A PBH would need to be smaller than about 20 tons in mass in order to capture significant color charge, meaning that its event horizon would be 10,000 times smaller than that of a proton. However, compared to other colored objects previously researched, these things could hold a lot of color change. In fact, a subset of these color-charged black holes called extremal or near-extremal black holes would form with nearly the maximum amount of color charge that black holes can theoretically have. In these cases, the internal color charge would counteract the internal gravitational field to the extent that the event horizon would be nearly nullified. Well, before we can begin constructing our colorful black hole detectors, we do have one more issue. The Hawking radiation causes all black holes to gradually lose mass. A black hole of at least 100 billion kilograms in mass could still exist today. Black holes leak more quickly the smaller they are. If a black hole had a substantial color charge, it would have long since vanished. In actuality, it takes 10,000ths of a second for a 20-ton black hole to vanish. Although it may not seem like much time, this was an aeon in comparison to the early universe's quickly changing state. Approximately 100 trillion times longer than the universe's age when those PBHs formed, that is. Indeed, those colored PBHs would be able to survive much into the end of the quark-gluon plasma period and into the era of color confinement when hadrons begin to emerge thanks to that 10 to the power of -4 second evaporation duration. At that time, they might have been the only objects in the cosmos with color charges. Do they maintain that color charge, though? Black holes that are electrically charged rapidly lose their charge, as I said. However, we have cause to hope that those early color-charged PBHs will continue to be charged. Keep in mind that these are extremely small, fewer than 10,000ths of a proton size. This indicates that they take in information very slowly. Additionally, a cloud of virtual colored particles from the quantum vacuum may grow around the colorful black hole, providing screening and making it act like an almost color-neutral hadron after the quark-gluon epoch is finished and the colored black hole is surrounded by color-neutral hadrons. It would be able to sustain its internal charge for a longer period of time since it would no longer draw opposing charges. Additionally, gravitational waves might have been left behind by this screening process, albeit they would likely be too high frequency and faint to pick up with the detectors we have now. The next phase of the universe's history, known as Big Bang nucleosynthesis, when the first light nuclei started to emerge from protons and neutrons, may have seen some of these black holes survive much longer. The near-extremal, or most colorful, black holes would be the ones that survive because they have the lowest Hawking temperature and evaporate more slowly. These could have disrupted nuclei formation and altered hadron distribution in a way that would allow us to detect a difference in the ratio of the quantities of light elements produced during that time. This would be the first indication and proof of this type that suggests any of this has truly occurred. There is a chance that the present cosmos contains color-charged black holes. According to some scientists, black holes cease to exist when their size hits the Planck length, the shortest measurable length, rather than completely vanishing. We refer to these as Planck remnants. Planck relics are primordial black holes that were formerly less than 1 trillion kilograms, and if there are enough of them, they may also constitute dark matter. And, if all I have explained is true, then these remaining Planck relics might have color charge. This is just one more if. Neutral Planck relics are nearly impossible to detect, so that would be fantastic. They might interact with atomic nuclei due to color charge, which would allow us to construct a detector. Even though it seems awesome, are these colorful black holes real? That chaotic first fraction of a second is not directly observable to us. But there is a strong theoretical foundation for their development, and if it is correct, it may have tangible consequences that advance our knowledge of the early universe. They might even aid in the resolution of the dark matter issue. All we need is for the universe's spacetime fabric to have been dotted with multicolored holes at the beginning. Please click the notification bell and subscribe if you would want to support this show.